All right. Today is the last day of new material. The next class will be just working on the study guide, and then the following class will be the final. So getting right down to the end. Anyway, we are going to finish out chapter 24 today. So we were talking about nuclear chemistry. Now, we had talked about something called transmutation. And that is when you take an element and change what it is. So, for example, if we take uranium 238, okay, and it changes, loses this alpha particle, and we are left with thorium 234. Okay, that's transmutation. Now, that is a spontaneous process. If you just have a chunk of uranium 238, that is going to happen by itself. Now, we also can do something called induced transmutation. Induced transmutation, which means we as humans have caused it to happen. Now, the example that it gives here in the chapter says we're going to take nitrogen, just good old nitrogen 14. And what we're going to do, we're going to fire an alpha particle at it. So we're going to add this alpha particle. And as it turns out, when we do that, what happens is we get oxygen. We get oxygen 17. Now, if you notice, these numbers don't add up. So what actually is going to happen as well, we only really got one of these protons and then the other two neutrons to stick. We actually lost another proton or hydrogen atom. Okay. So we can actually take nitrogen and change it into oxygen. It's called induced transmutation. Now we can do this with all sorts of different elements, but if we are dealing with larger elements, we call these the transuranium elements is what we're going to talk about. And this is, so uranium is element 92. Anything larger than uranium, so 93 through 118 currently is 118 is the highest we have. These are called the transuranium elements, and these are all generated by humans. We don't find these in nature. And how do we do that? Well, it's induced transmutation. We are going to take some element and we're going to start smashing them together, hoping that we can get them to stick, basically. Okay. So all of the elements larger than uranium, so 93 through 118, that's how they're made. We don't find them in nature. They are all radioactive. Some of them, their half-lives are extremely short. But that's what we do. Now, currently we have all 7 rows of the periodic table completely filled with named elements. if we discover new ones, and by discover, really, I mean make new ones by smashing things together and making something with more than 118 protons, then that will move on to the next period down, and we would start the 8th period. So anyway, that's transuranium elements induced transmutation. We are causing something to happen by smashing stuff together. Now, sometimes when we smash stuff together, it breaks apart. Other times, it sticks together. Okay. And we'll talk a little bit more about the differences between that here in just a second. But first, we need to address something that, well, violates another rule. So at the beginning of chemistry, we had this thing called the conservation of mass. And this was a very, very important rule. And we said, you cannot violate this. And it said, whatever mass you start with, you finish with. Okay? You cannot create or destroy mass. And that's what we were working with, that rule, pretty much all of the year. Well, once again, when we talk nuclear chemistry, things change. And so now we actually can change masses. We can make mass literally just disappear. And obviously, you know, this is a big deal. Right? We don't see this in regular, just everyday chemistry, and that's why we could use that rule for pretty much the entire year. In order to get rid of mass or gain mass or just change overall mass, we need to use what is probably the most well-known equation in existence. So that's Albert Einstein's favorite or famous equation, E equals mc squared. Now the m, that's mass. Okay, so this is how we are bringing mass into the equation. E, well, that's energy. And then c is the speed of light. We use c because light in a vacuum is a constant. So the speed of light is a constant, and what we can do, we can calculate with this change in mass what's going to happen. And what Einstein told us is that if you lose mass, where's it going? It has to go somewhere. Okay. Yes, we can make mass disappear, but we can't just poof it out of existence without any trace of it. Instead, we release energy. So we get energy that is being released when we get rid of mass. Okay. And what happens is, so when we do this, okay, yeah, all of these numbers add up, okay? But if you really get down to the nitty gritty, these two things have more total mass than this, okay? When you combine subatomic particles to make a new nucleus, they lose mass. They physically lose mass. Now, exactly why that happens and how that happens, that is a question not for high school chemistry. So we're not going to get into the particulars of that. Okay. In fact, a lot of subatomic particle research, we're still trying to figure things out. Okay. So, but anyway, the how and why you don't need to know. But yes, we lose mass. Okay. It's called the mass defect. Okay. So basically, and this is true for all atoms. If you look at, well, I mean, even just this right here, just before we do anything, okay? So nitrogen 14 has 7 protons, 7 neutrons. If you add up the mass of 1 proton times 7 and the mass of 1 neutron times 7, if you add all that up, it's going to be more than what we have here. And that's, like we said, called mass defect. And what happens is that mass is changed into energy. Okay. So, when you know the mass defect, you can put it into this equation and it tells you how much energy was released in order to form that. Okay. Speed of light, it's a constant, like we said, in a vacuum. It is on the front of the test cover page. So, anyway, we can calculate energy. Now, this is where the energy comes from when we deal with anything nuclear. Now, nuclear can be either mass destruction. Okay, we can see nuclear weapons that bring devastation, or we could be using it to power something. We have nuclear power plants, and we'll talk a little bit about that as well. But this energy comes from, well, we're changing masses. Okay? When we have transmutations, there's little tiny mass changes, and those mass changes result in energy. So, all right, now really, when we talk about nuclear reactions, there are 2 broad categories. 2 broad categories. We have fission and fusion. Now, fission happens with large atoms. If you have a large atom that is unstable, it's going to break apart. And if it's just radioactive decay, then that's just controlled emission. We lose an alpha particle. We lose an electron out of a neutron, turning it into a proton and stuff, like we talked about last time. But we can make an atom, instead of just decaying, split apart into 2 smaller things. Okay? And that is what we call nuclear fission. Okay? And in order to do that, basically, and this is outlined on page 879. So we take a neutron, and we smash it into something. The example that they give is uranium-235. Now, uranium-235 is very susceptible to fission, more so than the more common uranium-238. So we've got uranium-235. We smash a neutron into it. Now, at first, it joins that uranium, and it becomes uranium-236. Now, uranium-236 is highly unstable and breaks apart. And in this example, we see krypton-92 and barium-141. Now, if you notice, 92 and 141, those two mass numbers, they only add up to 233. So what happens to those other three? Okay, because our mass number was 236. Well, we get three neutrons that instead of joining in with either of those two new atoms, they do their own thing. Okay. And obviously we release energy with this as well. Okay. Now, what can happen? So remember, a neutron started this whole thing. So we started with one neutron, but then we released three more neutrons. So if those neutrons are released, they potentially could hit another atom, and that happens again. Okay, so potentially those three neutrons could turn into 9 neutrons. And if all of those hit, they could turn into 27 neutrons. Now, we always will lose some of these neutrons. We're not going to have perfectly efficient nuclear fission. Okay? That's just not something that happens. But we can get this chain reaction to continue on. Okay? Now, it doesn't always happen. We have to have the right type of material, and we have to have the right concentration, and we have to have enough of it to sustain this chain reaction. But if we continue this chain reaction on a large enough scale, that is what the very first atomic weapons did. Okay? Until basically this number of E got so big that it just blew everything apart. And obviously at that point, we no longer have enough material close enough to continue this fission chain reaction, but we had enough right at the beginning in order to get a massive release of energy. Okay? Now we can do this in a little bit more controlled manner in something called a nuclear reactor. So nuclear power plant, what is actually going on? We have these big heavy elements that are undergoing fission. Now we control it. Okay? We slow it down. We put special materials in there that can absorb some of these neutrons so it doesn't explode. Okay? We want a constant, steady rate of energy release. And what that does, well, this energy, in this case, it's heat. All right? We've got heat that is being released. Now, this heat can boil water. That steam is used to spin a turbine, which is attached to a generator. And so nuclear power basically takes this steam, spins a turbine, generates electricity. Okay? Then what they basically do is they use condensers to cool the steam back down so that it can recirculate. They don't release this radiated water just directly into the environment. Instead, they are releasing the water that runs through the condensing tubes, basically. If you've ever seen the cooling tower with steam coming out, yes, it is steam. Yes, it did come from a nuclear power plant, but it's not, heavily radiated. as it turns out, when you look at the history of nuclear power, it's pretty darn safe. Yes, there have been a handful of pretty bad accidents, but overall, nuclear power has a pretty darn good safety record. Um, and to be completely honest, it's a very clean form of energy. Um, Really, the only thing that is being put out into the environment on a constant basis is the steam, which, well, that's just part of nature anyway. Um, yes, I mean there is some environmental impact with mining the ores, and then we have to store them for a while as they cool off and things like that. Um, but yes,
Um, do you not have a class right now?
I'm doing class.
Oh, okay.
So, but anyway, now that is fission. Okay, that is fission. But the other category is fusion, and that's just the opposite. So instead of taking a big element and breaking it apart, um, we're taking small things and combining them together. The most common is where we take 4 hydrogens we smash them together, and we create helium. This is the power of the sun. This is what's happening in the sun on a massive, massive scale. Once again, we get mass defect, which releases a bunch of energy. And of course, just one reaction, the mass defect is pretty small. And so we don't see a massive amount of energy with one atom being created out of these 4. But it's happening on a massive, massive scale. And so all of that energy adds up. Okay. Now, it takes a whole lot to get this to happen. You can't just squeeze hydrogen with any methods that we have in order to turn it into helium. It takes a lot of heat as well. And when I say heat, I mean like 5 million Kelvin type of heat. So we've got this super heat, super pressure situation at the core of the sun, and that can fuse these together. Okay? That is why we call it a thermonuclear reaction, because it requires a lot of heat. Now it does release a bunch of energy, and hydrogen is incredibly abundant. So we would love to be able to use this for our power plants. The problem is, so far, anytime we've been able to do this on Earth in a controlled manner, now, once again, humans being humans, we did develop a bomb with this. So hydrogen bombs, this is what we have. But in order to try and generate power with this, which would be wonderful because, we start with hydrogen, which we've got a ton of. We get helium, which, hey, that's not a dangerous product at all. And then you get a bunch of energy. Be great. The problem is, so far, we have only, we can make this happen, but we have to put more energy into it than we get out of it. Now, the sun basically uses its massive gravity in order to generate these temperatures and pressures. And so that's why it can sustain this. But here on Earth, if we want to sustain it, we have to put more energy into it than we're getting out of it. So, anyway. Section 4 talks a little bit about just, how we can use radiation and things like that, besides just power plants and explosives. Anyway. The truth is radiation is all around us. Okay? Just existing, you are exposed to radiation. Now, some of it is dangerous, but most of it really isn't that big a deal. Most of it really isn't that big a deal. It is basically what we call non-ionizing, which means it's low energy. And so it doesn't really do anything to you. Things like radio waves. There are radio waves passing through buildings and people all the time, and it's not doing anything because it has very low energy. But if you get to high energy, then it can be a problem. It's called ionizing radiation because it can knock electrons off of atoms to create ions. Okay, and then those ions can react, which can make it dangerous. Anyway, the book talks a little bit about Geiger counters. Basically, it uses an electric charge to react with ions in order to see, is there radiation in the environment. So, we'll talk about just a couple things here. We're going to go through this section pretty quick. But yeah, uses of radiation. Obviously, we've talked about a couple, like we said, power plants, and unfortunately, humans have decided that they want to be able to kill each other with it too. So radio tracers. Basically, what we can do, we can take a different isotope than what is common for something, and when we put that into a system, we can trace where it goes because it is radioactive. It talks about using a radioactive form of carbon to figure out where these carbons are going when we do photosynthesis, or when plants do it, I should say. And basically, we can, follow an individual carbon atom based off of, hey, we've got this one that's a little bit different than the rest of them. It's basically like if you, are wanting to trace one thing among many, you make it just a little bit different. Maybe you paint it a different color and things like that, and you can follow it. So, we can also use that for medical imaging. Sometimes these radio tracers show up a little bit better on the image, so we can see the image a little better. We also can, if we look at things like tumors, tumors use a lot of sugar, and so we can basically put a radio tracer on a sugar, and that allows us to see where the body is sending a bunch of sugar, and that can help identify tumors. So, we do use radiation to treat cancer. Basically, radiation can damage DNA. So radiation can cause cancer by damaging DNA. But if we very specifically hone in on the tumor itself and just blast it with a ton of radiation, what happens is the DNA gets damaged to the point where the cells can no longer function at all, and they die. And so that's the whole point of using radiation to treat cancer, is we want to take these cells that have been damaged and basically finish the job. Okay, we are going to damage them to the point where they just cannot function anymore. So now, obviously, as we said, radiation is harmful, okay? In some ways. It can damage your DNA. It can, you know, I mean, a sunburn, that's damaging radiation. That's what it is. So you have to be careful about how much ionizing radiation you get. And so anybody who works with radiation on a consistent basis, they have basically little detectors that they wear all the time to measure how much radiation they're getting to make sure that they're staying within safe levels. There is, some charts that basically show at what dose do we start to see effects, and sort of some average exposure that you would see just in normal everyday life. Anyway, basically your normal everyday life, there is some exposure to radiation, but you'll be fine. Okay, largely because, well, the further away you are from a radiation source, the weaker it is. So, if you, like this marker, if it were right here, then that's going to have more impact than, well, if I set it over here and walk away. It's further away, the distance makes a difference. So, anyway, that is the end of chapter 24. And that's the end of new material for this class. Okay. Like I said, in the 2 days that we have left, we have one that is for studying for the final, and then we have the final itself. So, I'm not going to assign homework for this section. It's mostly, I would rather you take the time to get ready for the test instead of do one more homework assignment. So, with that, we will finish up.